The next type of transmission line system in the classification is the medium transmission line. So far we have seen the short transmission line which is below 20 km. So the medium transmission line is below 80 km. For medium transmission line, the distance is between 80 km to 250 km and the voltage level is from 20 kV to 100 kV. So the basic and the very important point we have discussed in the short transmission line is the neglecting the capacitance. Neglecting the capacitance effect. So in the ABCD parameters, the parameter called C will be 0 because there won't be any shunt capacitance. So the capacitance effect will be 0 in short transmission line because of the lower distance. When comparing to the higher distance, that is above 80 km to 250 km, line capacitance and the shunt capacitance will come into the act of medium transmission line. Both line and shunt capacitance will come into the act of medium transmission line. So calculating this capacitance for the medium transmission line is very important. So to calculate this capacitance, we have three different type of methods which is called as normalized method to find the capacitance of the medium transmission line. They are end condenser method, nominal T method, and another one is nominal pi method. So we are going to discuss about this nominal T and nominal pi method, how the capacitance will affect from if we are considering this nominal T method, and how the capacitance will play if we are considering this nominal pi method. So these two methods we are going to discuss. If we consider a transmission line from sending end to receiving end, the transmission line, the capacitance effect will be there. Starting from the point of sending end to the receiving end, the capacitance effect will be there. So this is the sending end voltage Vs and this will be the receiving end voltage Vr. Okay, the capacitance may vary from sending end to receiving end. This charging current of the capacitance will be line capaciting current of the particular point of the transmission line will be the line charging current of the sending end voltage. So from this we can conclude that the C1 will be greater when compared to other capacitance. So in order for simplification and calculating the capacitance method, we are calculating that the capacitance will be either it is present in between or it present at the end of the transmission line system. So from this they are classified into nominal T and nominal pi method. So from both of this method we are going to discuss the phasor diagram and how the equivalent circuit will be in nominal T and nominal pi method, and what is Vs, Vr, Is, Ir relation in the that is the ABCD parameters of these system. Okay. So the first one is nominal T method. So in nominal T method, so this is my sending end voltage Vs and this is my receiving end voltage Vr. As the name suggests T, some parameters will be there. So here I am placing the capacitance. So this is the capacitance of shunt admittance Y. So with this capacitance I am going to calculate the Vs and Vr, Is, Ir relations. So we already discussed the transmission line has some parameters like R, L and C. So C we have shunt capacitance we have placed at a distance. So the R and L parameters are divided by 2 for the whole transmission line. So this is R by 2, L by 2. Nearer to the sending end voltage I will differentiate with S, Rs by 2 and Ls by 2. Similarly, this is Rr by 2 and Lr by 2. The whole I can call it as Z by 2. Z is equal to R plus Jx. So Z is Z by 2. I can in the whole I can call it as Z by 2. That's the whole impedance is divided into 2, and the middle of that transmission line I am placing the capacitance. Now I am going to find what are all the parameters and how the values of Vs and Vr will be. So the first one we will put the current one. From Vs the current is Is, So to the VR, the current will be IR. So this, the current is IC. So the voltage at this point will be V dash. Okay. So from this, the first point we can conclude by using KVL. What we have to find is Vs Is, which should be in terms of VR IR, and this is also in terms of VR and IR. This is our ultimate decision, or our ultimate path to find the Vs and Is in terms of these, to find the ABCD parameters. So what is Vs? So Vs is, I can write it as V dash plus Z by 2 into Is. Fine. What is V dash and what is Is? We have to calculate. So Is is equal to, by KCL, I can write it as IR plus this is C, right? Okay. IR plus IC. IR, that is okay, I can't differentiate further. IC, to proceed with IC, IR plus IC in terms of shunt admittance, so Y into the particular voltage V dash. So I am having V dash here and also V dash here. So I want to find what is V dash to substitute in this both equations. So V dash is equal to VR plus, what is the current here? It is IR into Z by 2. Okay, this is equation 3, this is equation 2, and this is equation 1. I am substituting 3 in 2 and 1. Therefore, Vs is equal to, what is V dash? VR plus IR into Z by 2 plus Is into Z by 2. Similarly, Is is equal to IR plus Y into, what is V dash? It is VR plus IR into Z by 2. So I need the equation for Vs in terms of VR and IR. So I am substituting Is. Therefore, Vs is equal to VR plus IR into Z by 2 plus IR plus VR into Y plus IR into ZY by 2. Fine. Now rearranging this equation in a simpler form, Vs is equal to VR into 1 plus Y plus IR into Z plus ZY by 2. Similarly, Is is equal to, for VR it's simply Y, and for IR it is 1 plus Z by 2. Okay, when writing in terms of ABCD parameters, so Vs, VR, IR, Vs is equal to VR, substituting Is here, so multiplied by Z by 2. Therefore, Vs in terms of VR, IR will be 1 by ZY by 2. This is Y and this is Z into 1 plus ZY by 4. Taking Z as common in this two term, that will be Z into, when it comes Z, it will be Z plus ZY by 2, and taking Z as common, and here it will be 1 plus ZY by 2. You have to multiply by Z by 2, and here it will be into Z by 2. So with simplifying this, we will get the ABCD parameters as this. So A is equal to 1 plus ZY by 2, and B is equal to Z into 1 plus ZY by 4, and C is equal to Y, and D is equal to 1 plus ZY by 2. A and C will be common, and this term in terms of short transmission line, this term becomes 0. Now it becomes Y because of the presence of the shunt admittance Y value. So from this value we will calculate the Vs and Is value with respect to VR and IR. When going to the phasor diagram, when I keep VR as reference, this is VR, IR will be, this is the capacity, IR will be lagging VR at a angle pi r. Then parallel to this IR, the drop will be there, which is IR, that is receiving end into with respect to R. Here the total line parameters is divided into two halves, so IRR divided by 2. So with 90 degree phase shift, the loss will the losses will be IR into X divided by 2 with 90 degree. When joining these two, it will give the V dash value, that is the voltage across the shunt capacitance. Then again the losses in the sending end voltage with respect to R, that is ISR divided by 2, here I into S X by 2 will give you the sending end voltage, sending end voltage Vs. So with Vs lags by an angle pi s will give you the Is. The next type to find out the capacitance of the transmission line is, so far we have seen the nominal T method, now it is the nominal pi method. So this will give this T and pi will give the arrangement of capacitance in the transmission line. So from pi, if we consider this as a transmission line, therefore two capacitance will be there. So this is my capacitance near the sending end voltage, and this is my another capacitance at the receiving end voltage. So this is my Vs and this is my Vr. So now where I am going to place my transmission line parameters R and X. In the previous method, we have divided into two. In the center of that we have the capacitance, and both the sides we are having the transmission line parameters R and X. In this method, we don't divide the transmission line parameters. Simply we are placing the R and X in between these two capacitance, which is placed near the sending and receiving end respectively. So now we are going to calculate what is same as that of the previous topic. Yes, what is Vs and Is in terms of Vr and Ir. So Vs, Vr, so here the current will be Is. In the previous method, we denoted this current as IC. Now this IC is nearer to my sending end voltage, so I am denoting it as ICS. And this is my receiving end current, that is IR. So obviously this will be ICR. Fine. This is my, I will denote this capacitance, that is the shunt admittance, with this symbol. Now I am not going to divide the transmission line parameter. Instead I am going to divide the capacitance, that is Y by 2, and this is Y by 2. In the previous section we have divided the transmission line parameters R and L along the length of the transmission line into two halves, being the capacitance with a single capacitance. In this we are dividing the capacitance into two. So this will be R and this will be your X. So this is Is, this is ICS, this is IR and ICR. So then what will be the current here? This is I dash. If you are able to relate with the previous problem in nominal T method, we started with V dash, that is the voltage across the shunt capacitance. Now the current that is flowing through the transmission line parameters R and X will be I dash. So the first step, by differentiating with that and comparing with the previous method, we are going in the flow to find out the I dash. So I dash is equal to, by using KCL, it will be ICR plus IR. Okay, fine. Then the next one is Vs. Then Vs is equal to, here the receiving end voltage is Vr, and now I am considering the whole transmission line parameters. I am not including this capacitance. So Vs is equal to Vr plus what is the current here? It is I dash into R plus Jx will be there. I am writing it as Z. So Vs is equal to Vr plus I dash into Z. Okay. Then we know what is I dash, right? So Vr is equal to I dash is equal to ICR plus IR. This is capital R, right? Yeah. Okay, IR into Z. So I want my equation considering the parameters VR and IR. So I don't want this ICR. Instead, I want to find out what is the value of ICR. So ICR is equal to VR plus ICR is equal to what is the voltage across this ICR? ICR, ICR, the voltage across it is VR and the shunt admittance is Y by 2 plus IR into Z. Rewriting this equation, VR plus VR Z Y by 2 plus IR into Z, which is VR into 1 plus ZY by 2 plus IR into Z. So this equation I have achieved in the terms of VR and IR. The next is I want to find IS. So what is IS? IS is equal to ICS plus I dash. So IS is equal to ICS plus I dash. I already know what is I dash, right? We will substitute for ICS also. For ICR we have substituted VR Y by 2. So similarly for ICS the voltage across that is Vs, but we want the equation in terms Vs, so Vs into Y by 2. So Vs into Y by 2, okay, plus I dash. What is I dash? I dash is equal to ICR plus I into R. So now I am having Vs into Y by 2 plus ICR is equal to VR into Y by 2 plus IR. Okay. I want equation in same VR into IR. I don't want Vs. Instead, I am substituting what is the value of Vs. We have already calculated that as VR into 1 by ZY by 2 plus IR into Z plus this term VR into Y by 2 plus IR. So simplifying this equation, I am taking Vs. So this term into Y by 2 will be there, right? So VR Y by 2 plus VR, if I take Y by 2 as common, then it will be 1 plus Z. If I take plus VR Y by 2 IR into 1 plus Z. So I am taking VR, this Y by 2 and Y by 2 becomes Y. So VR Y. So I am taking VR as common. So this will be Y1 and bringing to this equation it will be Z and Y by 4. 1 plus ZY by 4 plus IR into, here also it will be Z by 2, right? Sorry, Y by 2. Y by 2 and here it will be R. So 1 plus ZY by 2. Okay. So this is IS. So I am rewriting this equation Vs IS in terms of VR and IR. So Vs IS in terms of VR and IR. So 1 plus ZY by 2, here it is simply Z, simply z, and here it is y by y into 1 plus zy by 4, and here it will be 1 plus zy by 2. This is the ABCD parameter. So going to the phasor diagram, similar to that of the nominal t method, here I am having VR which is my base, and the IR will be of some angle from the VR, that is pi r. So now I am having, so with the losses will be, there it will be r by 2, here the current will be I dash, the current here will be I dash into r, and with respect to 90 degree the current will be I dash into x. So connecting these two equations, it will give the sending end voltage. So sending end voltage is nothing but the receiving end voltage plus the losses occurring in that transmission line. So Vs which is lead by an angle phi s from Is. So Vs Is plus Ir, Is is equal to I dash plus ICR, where I dash is equal to ICR plus IR. Is is equal to ICS plus I dash, where I dash is equal to ICR plus IR. So similarly, Is is equal to ICS plus ICR, then IR it will come. So Is, so this I can write it as IC. So Is is equal to, this is the term IC, so these three will account for the current Is, that is the sending end voltage, and from that which is lead by the current ICS, IR which is lagging the capacitive voltage ICR, and Is which is also lagging the capacitive line current, that is ICS. The next type of classification is the long transmission line type, that is for medium transmission line it is 80 to 250 km, for long transmission line it is above 250 km, and the voltage level is greater than 100 kilovolt. So in this long transmission line we can't do simplification with the particular value as we do in the medium and short and medium. We have definite values of I and Vs, Is, and in medium also we have different value of Vs and Is in terms of Vr and Ir. In long transmission line, as the name indicates, we can't conclude how long it is, so we are calculating the whole voltage and current of the sending and receiving end voltage at a particular distance with the parameter x. So we are going to calculate the voltage at a particular distance x. So from this x, by substituting the values, we can determine what is the voltage level. So in this we are going to calculate what is the voltage at a particular distance x. But for considering that, the equivalent circuit will be, here the capacitance will be distributed throughout the transmission line. So this is my sending end voltage and this is my receiving end voltage Vr. So from receiving end at a particular distance called x, so this is x. So from receiving end at a particular distance called x, I am having the transmission line parameters R and L. Okay, so this is Rx and this is Lx. So with the differentiate with respect to the distance x, I am considering this as z of del x, where del is the difference in the distance, z of del x, and the current flowing at this point is I of x. Fine. So here it is will be IR and here it is IS. Then I am having my shunt admittance y. This is z into del x, this is y into del x. Okay. This del x is at the point of this shunt capacitance is at a point of del x, that is a small differentiation with respect to the distance x. I am having this capacitance with shunt admittance y, and the distance will be del x. So this is z into del x, and the shunt capacitance will be y into del x. So what is the voltage that present at the point of my shunt capacitance? That is V. Of course, it is at the distance x. We are going to calculate Vx. My shunt capacitance is at the distance Vx, and it also includes the value of the distance del x. So x plus del x. So the current flowing at this point will be I of x plus del x. From the receiving end, I am fixing a point at a distance x. At that distance, I am having L and R. So this L and R will have the distance of del x. So at the del x from the x, I am having my shunt capacitance. So the value will be y into del x and z into del x. Z at the distance L, z means R plus L, which is constitute the z, and the distance they are imposing is the del x, and the shunt capacitance is at the distance del x. So y into del x and z into del x. So these parameters are over. Now we are going for the voltage and current value. The voltage is x plus del x. So similarly, the current will be I into x plus del x. So the first step we are going to do is the KVL. So KVL at this point, V of x plus del x is equal to, V of x plus del x is equal to, I have to know what is, if this is V as x plus del x, what is this voltage? That is V of x. So V of x, what is the current flowing here? Flowing at this point, that is Ix into Z into del x. So the first equation is V of x plus del x, which is equal to, the current here is Ix into Z into del x into V of x. So rearranging this equation, V of x plus del x minus V of x divided by del x, which is equal to Z into I of x. So I am imposing this del x limit to 0. So this term will be the d of V of x divided by dx, which is equal to, there is no del x here, so similarly Z into Ix. The next step, I am going to do the KCL for this term. So I into x plus del x is equal to, what is the current here? It is I of x plus, I have to know the current through the capacitance. So it will be y. In order to find the current, I should take the voltage. So what is the voltage? V into x plus del x. So rearranging this equation, I of x plus del x minus I of x divided by del x. So same term, in order to find the limit of del x is equal to 0, here I am having y v x plus del x. The same step, I am putting del x to the limit of 0. This equation will be d of I of x divided by dx, which is equal to, here also I am having del x, I am putting this del x limit as 0. So it will be y of v of x. So this is my first equation and this is my second equation. So differentiating with respect to x in these both two equations, so 1 and 2, I am differentiating with respect to x. So the first equation will be d square v of x divided by dx square, which is equal to, when I differentiate this, it will be z into d into I of x by dx. So what is d into I of x by dx? It is y into v of x. So z y into v of x. Similarly, I am differentiating this equation, d square I of x divided by dx square is equal to y into d into v of x divided by d of x. So what is this term? It is equal to z into I of x. So y z into I of x. So from this term, if we know what is the value of the z and y, we can able to find what is vx and ix. So vx and ix, this is the voltage and current of the long transmission line at a particular point x. If we substitute x is equal to 0, then it is the receiving end voltage, because we are taking the value of x at the point starting from the receiving end voltage. If we substitute x is equal to 0, we will get what is the value of the voltage at the receiving end. If we substitute this x is equal to L, that is the total length of the transmission line, we will get the sending end voltage. Okay, from this we will get the Vs and Vr voltage, which is the basic need, and this is the transmission line, long transmission line procedure. Here we are not taking account of the distance of a particular distance, we are taking the distance as x and substituting the value of the distance and finding the particular voltage and current level at that distance. Thus our unit 2 is getting over. A short summary of what we have seen in the unit 2 is the first unit we have seen what is R, L and C with a brief introduction, and in the second unit we are going for the short, medium and long transmission line. In short, it is what is the voltage level and what is the distance associated with that, and medium and long how they are classified, and what is the difference between short and medium, what is the major difference, that is the neglecting the capacitance. And in medium we have gone through two types, that is nominal T and nominal pi method to find out the capacitance. In long transmission line we have fixed it at the distance x, and with that distance x we are going for Vx and Ix. And another topic which is in the unit 2 is the Ferranti effect. Thus unit 2 is getting over. In the next lecture we are going for unit 3. Thank you.